Welcome to The Explainer. Today, we're diving headfirst into the wonderfully strange world of prime numbers to uncover a result so elegant, so beautiful, that the great mathematician Carl Friedrich Gauss himself called it his golden theorem.
Okay, so let's jump right in. We're going to start by looking at this mysterious pattern that mathematicians have been staring at for centuries. It all kicks off with a really simple-sounding question about prime numbers and perfect squares.
So take a look at this. What's so fascinating here is the strange symmetry, right? This whole table is basically asking, for any two prime numbers p and q, is q a perfect square in the mathematical world of p? R means yes, it's a residue, and n means no. But check out the pattern. For some of these pairs, the answer for p comma q is the exact same as the answer for q comma p. You can see they're perfectly mirrored across the diagonal. But for other pairs, it's the complete opposite. An r on one side corresponds to an n on the other. This is, well, it's way too organized to be a coincidence.
Yeah, this is not random at all. There's a deep, incredibly elegant rule pulling the strings here, a secret connection between any two primes. But to really get it, we first need to learn the language it's written in. So let's decode those key concepts. Turns out, we only need a couple of ideas to unlock that entire table. It's simpler than you think.
First up, modular arithmetic. You've probably heard it called clock math, and that's a perfect way to think about it. It's a world where numbers just wrap around. The entire pattern we just saw lives and breathes in this world, where all we care about are the remainders you get after dividing by a certain prime number. And inside this clock world, some numbers happen to be perfect squares. We give those a special name, quadratic residues. That's the R from our mystery table. All it means is that you can find some number x that when you square it, you land on q on your p-hour clock.
Okay, to make this super clear, just picture an 11-hour clock. The number 4 is a residue because, well, 2 times 2 is 4. Simple enough. But get this, 5 is also a residue. Why? Because 4 squared is 16, and if you go 16 hours around an 11-hour clock, where do you end up? Right on 5. But then you have numbers like 6 or 7. You can try it yourself. Square every number from 1 to 10. You will never, ever land on 6 or 7. They are non-residues. So mathematicians got a little tired of writing out that whole long question over and over again. And you know what they did? They came up with a neat little shorthand, the Legendre symbol. Now this thing that looks like a fraction in parentheses, it's not division. It's a question. It's just a super compact way of asking, is it an R or an N? The answer is +1 if it's a yes, and -1 if it's a no. Okay, now that we're armed with this new language, we can finally go back to our mystery table and reveal the hidden rule that Gauss figured out. This is the good stuff.
So the real question is, how on earth are these two things related? How does knowing if prime p is a perfect square in the world of q tell us anything about whether q is a perfect square in the world of p? I mean, they seem like two totally separate, unrelated problems, right?
And here it is. This is the answer, the Law of Quadratic Reciprocity. I know, it looks a little intense with all those parentheses and exponents, but what it's saying is honestly one of the most shocking and beautiful truths in all of number theory. This is the formula, the secret key that directly links those two seemingly separate questions. This one formula perfectly explains all those weird patterns we saw. It all boils down to that exponent on the right side. See, any prime number, besides 2, is either 1 more than a multiple of 4 or 3 more than a multiple of 4. Now, if at least one of our primes is a 1 mod 4 type, that exponent becomes an even number, and -1 to an even power is just +1. That forces p over q and q over p to have the same sign. Boom, perfect symmetry. But if both primes are 3 mod 4 types, the exponent is odd. That makes the whole thing -1. Forcing the two symbols to have opposite signs, and there's your perfect antisymmetry. It's amazing. Even Gauss himself, the first person to actually prove this law, called it the fundamental theorem. He knew right away that he had stumbled onto something incredibly deep, something truly important about how numbers work.
So why does this all matter? I mean, is it just a pretty pattern? Absolutely not. This law is actually an incredibly powerful tool for calculations. It has this secret superpower. It lets us take a really hard problem, like asking about squares on a giant 1,000-hour clock, and literally flip it upside down to turn it into a much simpler one.
Let's actually see this thing in action. Let's say we want to know if 41 is a perfect square in the world of clock math, modulo 2027. I mean, That is a huge clock. Checking every possibility would take forever. But with reciprocity, we just flip it. Instead, we ask, is 2027 a square modulo 41? Well, we can easily find the remainder when you divide 2027 by 41. It's 18. So our huge, scary, impossible question just became, is 18 a square modulo 41? And that is a vastly simpler problem to solve. It's a total game changer.
But really, the true legacy of this theorem goes way beyond just being a clever calculation trick. It was like opening a doorway into a whole new universe of mathematics.
If you want to know how important this theorem is to mathematicians, just look at this number. How many different ways can you prove something is true? For this one theorem, there are over 240 different published proofs. Think about that. Each proof reveals a new connection, a totally new angle on this deep, fundamental truth.
You see, the quest to understand why this law works and how it could be applied to other, more complicated number systems was a huge driving force in mathematics for centuries. It literally helped create entire new fields, like algebraic number theory and class field theory, and it even laid the groundwork for massive, modern research programs that are still trying to find even deeper, unifying patterns today.
So what you should really take away from this is just a sense of wonder. The idea that even in something as basic as prime numbers, there are these beautiful hidden laws that connect everything together. The Golden Theorem shows us that the mathematical universe is just filled with these secret symmetries waiting for us to find the right language to see them.